Our topic tonight, Containers 101. I could subtitle this, Understanding How Containers Work to Work Better with Containers. That's me, Brent Laster, and I have a training company in addition to a day job that I do, but I have a training company, Tech Skills Transformations, and really enjoy being able to do events like this and to try to share some of what I've learned over the years and some ways to think about things as well. So starting out, how many people have used Docker before? All right, how many people understand Docker? All right, these are the people who are going to answer questions when we get to that time, right? Okay, just to clarify. No, if you haven't, if you've used Docker, or you've used containers before, you probably have used them and have learned enough to kind of understand what they are used for, and you have this sort of idea they're kind of a black box that just happens to work. And there's something that's big in the industry now. We talk about things like Kubernetes, some of these buzzwords you've heard. I wish we had time tonight to get into all that. But really what we're going to try to do in this presentation is in the time that we have to give you kind of an explanation of what containers are and kind of how they work. There's a seat up here at the front. To talk about how what they do, how they're put together, those kinds of things. And if we have time, we can get into even a little bit deeper on how they're implemented in the operating system and that sort of stuff. But I don't want to dive too deep in the short time we have here and kind of make people's heads explode here. So one thing I'll say about questions, if you have questions, I welcome questions. It does, I think, work a little better for me if you can hold them till the end of the 45 minutes. I know that can be a long time, but I say that just because I want to make sure that I can get through the material for everybody and not interrupt the flow too much. And sometimes what I find is that people have questions that will also be answered when I am going through a later slide or something like that. So please do queue up your questions with that. We'll get to those at the end of the sessions. And if you guys can help remind me, you have a task here to help remind me that when we ask a question in the room here, that I repeat it back so that everybody online can hear it as well. Okay. And by the way, a quick shout out to Out the Barn and the folks who've done the sound and also the web Zoom folk set up here. It's great that we're able to do this sort of hybrid environment. Really nice that we can do that to make it both in a live and a virtual event. All right. So about me, quickly, just a little self-promotion here. I have a training company, as I said. My day job is as an R&D DevOps director. Actually work at a company called SAS up in Cary, North Carolina. You may have heard of it before. A global trainer, do training, get Jenkins, Gradle, all sorts of fun stuff. Couple of articles out there, opensource.com, also on a couple of books and such. And there's some information. If you're interested in connecting with me on social media, feel free to do that. Always happy to connect with others there. So a couple of quick books here. Professional Git. I do a lot of training in Git as well. If you are interested in learning more about Git, either as someone who is fairly new to the using Git or someone who's more advanced in it or wants to learn some more tips and tricks, maybe check that one out. Also, there's a Jenkins 2 book if you're interested in CI/CD and using Jenkins as a workflow and as a pipeline orchestrating tool there. Check that one out as well. If you get that one, I'd suggest getting probably the online version. As a printed version, some of the screenshots are kind of washed out in that. Have quite a few courses on O'Reilly as well. If you're interested in any of these sorts of topics, Kubernetes, any of these kinds of things, check out, just search for my name and it'll come up as well. All right, enough about me. What we're going to talk about tonight is our containers. What containers are and what are the benefits they provide. We all hear the term containers. We know it's a buzzword. We know that it's popular. We know that we need to know something about it today to really be in the tech space and to really be doing the kind of cool stuff in there. So we'll talk about what they are, the benefits. We'll talk about how they're constructed. So how is a container really implemented? What are the basic sort of building blocks of it that are come together to make up this thing we call a container? And especially what is it as compared to some of the lower pieces of it, the images and the layers, these kinds of terms you may have heard in passing. We'll see how that all kind of comes together to form a container. We'll talk about this idea of immutability. If you've been around containers at all or Docker, you've probably heard this term tossed around, immutability. Kind of a funny word, but it basically means that we are something that is not changeable. It's not updatable in the same way we might think about just creating a new one or a new thing, updating it. we would have to create a new thing instead of being able to update it. We'll talk about the core Linux functionality that containers are based on. So containers, even though this is the sort of the hot topic these days, and we're talking about Kubernetes and different pieces, container technology has been around for a long time. It's been a part of the Linux operating system since way back. And we'll talk about a few of the core technologies in Linux that actually allow containers to work, to give you a better understanding of this. The idea, by the way, of this presentation is not that you come away understanding everything that we say, but that you've been exposed to it and that you have some ideas and ways to think about it so that you can take those and then do some more learning on your own. I'm a firm believer that no matter how well somebody may present a topic or not, you still are learning on your own. When you're doing the hands-on, you're still getting out there and exploring it there. So I hope that you'll take some of the material that we talk about tonight. I'll make the slides available. I hope that you'll take the opportunity to explore it some more on your own, ask some questions, even reach out to me if you have questions that you want to follow up on. We'll talk about how containers reuse code. We'll look at storage driver for, I said Docker, so it should be single Docker. But what storage drivers are the things that allow the container to come into existence. By that we mean pulling all the pieces together, kind of tying everything together, weaving it all together to make up a container, all the pieces it needs. So we'll talk about storage drivers, and we'll look in particular at one called the overlay 2, which is sort of the current one that's used in most cases. There's a long history of storage drivers, which I won't bore you with tonight, but the overlay 2 is kind of the common one. And then finally, we'll talk about the Open Container Initiative. This idea that Docker is not the only game in town anymore, but rather that we actually have this specification that allows other players to be in this container space and to work with it. So it sounds like a lot, but I think we can get through it in the next 45 minutes or so. So let's start out talking about what are containers. So a container, a couple ways to think about it. One is as a standard unit for delivering software with the virtual environment to run in. What do I mean by that? Well, if you think about when you get a container down, you're not just getting a piece of software, you're getting the environment that is actually set up to run it with. There's an operating system, there is any kind of libraries, there's an environment in there set up. It's almost as if you had a computer with just one dedicated application on it. If you had a laptop or something that only ran one specific application and had that environment and had that setup that was tuned for that application. That's kind of the same idea when we talk about containers. So another way to think about it, though, is sort of this standard unit where we can sort of package up software and we can give the image or to somebody else and they can spin up a container and get that same functionality. In the same way you might pass a laptop with something to somebody else and say, here, go run it, go use it, and you're good to go. Functions like a fully provisioned machine. It has all of the software installed on it that's needed to run whatever the application is that you're focused on there. So again, it has all the pieces on it, and we'll look at that more in just a moment. It's a way of packaging software so that it has a self-contained environment to run in. When a container is running on a computer, running on a system, could be a virtual machine, could be what we sometimes call like a bare OS, an actual physical machine with the software installed on it, to the application running in the container, it appears that it has its own environment. It appears it has its own setup, its own everything in there that actually allows it to run. In reality, what's happening is we are carving out some of the resources on the system to allow that containerized environment to be executed and the application to run. So we're actually carving out portions of the operating system's resources to give to that container, and that container then has an environment of its own in there that tells it how to run and then runs the application. So let's look at a picture. If you work with containers for any length of time, you will eventually see the obligatory container cargo ship picture there that you have that's showing the idea of the containers, the cargo containers. That is these boxes that are self-contained. They've got something in them, but we can move them by the container itself. We can move everything that's in there with it. So what's in a typical sort of software container? Well, kind of comparing it to these cargo boxes, you can have things like the app, you can have things like the runtime, the dependencies in there, of course, the settings, into the system libraries. Again, all the kinds of same things you might have system tools on an actual machine where you were running this application. These are just packaged up in this containerized environment. So that gives you a container, and there's the mascot for Docker. Docker is sort of the most widely known container orchestration piece, container manager. And it's that picture of a whale there with the sort of cargo's containers on its back. So the container, though, is not a VM. By VM, we mean a virtual machine. If you've used anything like a virtual box or any kind of hypervisor, a program that allows you to run a virtual machine on your system, this is not what that's not what a container is. A container, instead of having to rely on another program to run there, is actually carving out those operating system resources again to make things work. Containers are running instances of what we call images. We're going to talk more about what images are in a minute. And images are basically, though, what define what goes into a container. It's the pieces, it's the programs, it's the environment settings, it's whatever it takes to build up that set of software or that configuration in that container for it to be able to run the application. We talk about benefits of containers, and lots of words on the screen, too many words probably, but the couple of basic benefits here: easy to create and deploy once the image is defined. If you think of it again as you have this self-contained package that already has everything configured in it, you don't have to go through and install software, you don't have to go through and set values, you don't have to go through and and put the application, find the version of the application. It's all wrapped up in that package. So with that, it's easy to create and deploy once you define an image. We're going to talk in a few minutes and show you kind of how this container is created from the image. Think of the image as sort of the basic set of things that you have that you want to run, and then the container as being the running instance of that. It's best practices of continuous deployment, integration, deployment, reliable builds out there. So it's easy if you get these things, these self-contained environments. If you think about it maybe from a CI/CD pipeline perspective, this idea of continuous delivery where we're trying to put software, taking source code and we're building it in an environment with a certain kind of compiler, a certain kind of environment there. You could certainly code that up in a pipeline and have that working, or you could have a container that actually has the compiler in it, has all the environment in it, and you could just spin up that container, send the source code to it, have it built, have it then the output written somewhere else. So it's with containers, it allows us to really sort of separate the versions of things that we want and the environments they run in so that we're not having to rely on having to set that all up on one system. Instead, we can fire up a container that has the elements we want in it, the software we want, and then use that to create things. Quick and easy rollbacks due to image immutability. If you have a previous version of an image and if the current one has a problem, you can go back and just get the previous image and actually fire up a container from there. Created at build release time instead of deployment time. So applications are decoupled from the infrastructure, meaning that basically it's got everything it needs to run, so it's going to start up there, and you don't have to take a lot of time to configure everything, set up the environment. Provides observability. I'll skip over some of these, but basically you get the idea. It's portable across any kind of OS or cloud that supports containers. So if I have any system that has something like Docker on it, or these days more like the OCI runtime interface, then you can take your container, you take your image, and you can spin it up on any of these machines. So it becomes portable. So it's not just about porting an application, it's about the application and all of the pieces that are used to run it. So resource isolation and hopefully effective utilization because things are wrapped up and so on. What is a container image? We said that containers are based off of images. When we talk about a container image, it's a read-only template used to create a container. We're going to show you a picture in a minute, kind of how this goes from a text file that describes the sort of recipe or the steps through this that we want to use to create it, that we can use to create an image, and then how that gets turned into a container. But container images are kind of like a snapshot of a container. So the best way I can kind of explain this, and I use this analogy when I talk about containers a lot, is if you think about if I am setting up a machine, I am provisioning a system. Maybe you've done this at work. You had to provision a PC or a system, or maybe, how many of you are tech support for somebody in your family? Yeah, all of us, right? At some point probably in there, have had to set up a machine for somebody or do something with that. You go through and you install the software, right? You maybe install the operating system, you install any kind of Office applications, Microsoft Word, those kinds of things that the person wants on the computer. You're putting the software on the disk. Eventually, that disk has an image of all of the software that we want on that computer. No one may be using it right then, but that image is built up. That image can be backed up, it can be used to build other machines and so on. So we create an image that has all the software on it, and during the process has the configuration on it. It's been added into directories, directories have been set with paths, those kinds of things. So we build up an image. Now, when we actually turn it on and use it, that's kind of like a container. So the image is building up these sets of things that we want to have in our container, that we want to be available when we turn it on or when we run it. Think about it that way. Images are stored in a registry. You will hear probably of container registries. So these are places where we store images out there. The biggest one is the Docker Hub, and there are all kinds of images out there. So if you're looking for a container to do something, you go out and find the registry, and then you can download the image, and then you can spin it up and run it as a container. Now, you can have these registries inside of your business or inside of a company. You can even have your own local registry on your own machine if you wanted to. It's just a place to store images, much like a source control system like Git or something is a place to store source code. Images are generally considered to be immutable. This is kind of that funny word I said before, which basically means that once you create an image, you don't change the image itself. You go and create a new one if you need to make some change. And we'll explore why that's useful or why that is the case in just a moment. Container images are built up from layers, and the Docker build command for using Docker is used to create images. So let's get into some pictures here. I like pictures. So on this one, and talking about what is an image layer. So image containers come from images or running instances of images. Images are built up of layers. So when we talk about a Docker image, each layer, it basically results from the instruction in what we call the dockerfile. We're talking about Docker here. Now, the dockerfile is simply a text file that gives you kind of a step-by-step process here to go through and put things into the image. Now, I say each layer results. Not all instructions in a Dockerfile will create a new layer. It used to be the case as they've kind of optimized it since then. But if you look kind of at the top right here, you can see a Dockerfile, an example here. And it says something like from Ubuntu 18.04, then a copy, then run, then a command to run from there. Now, if you think about this from the same standpoint of the example we were just talking about, where you're setting up somebody's computer, you might have a list from that person, if you're doing it for a relative, for example, which says, hey, I want you to install the Windows 10 operating system, and then I want you to actually copy over some personal files that I have on a USB drive, and then I want you to set up an environment like this or something like that. That same kind of idea with this text here in a Docker file. It's a sort of sequence of steps that tells it how to construct the image that you can then run a container from. Again, think about it from the standpoint of these are the kinds of things that you're putting into, like you would put on a disk on a computer. So each layer basically creates its own, or each instruction there basically results in a layer, most of them do. And layers are stacked on top of other ones. Each layer is only the set of differences from the last one. So if it has some files, you think about each layer having its own set of files or some sort of configuration has been done, then you only have to do the next step in the next layer. Each layer is read-only except for the last one. And by that we mean as we're going through and we're creating these sets of layers that define what's going to be in the image, when we actually go to run this image as a container, what really happens is it just gives us another thin layer on top of the image, and that's how we get the container. Now the trick is that thin layer on top, that's the thing where you read-write. That's the read-write layer. Everything else is read-only. The way that I think about this, kind of going back to our analogy here, we talked about setting up somebody's computer. You think about, you install all the operating system, you install the applications, people are generally not going to be writing or making changes in those areas, not in the system area where it's installed. Instead, they have their own user space that is their dedicated, their home directories, whatever it is, that has their place where they can make changes and they can read and write and create content. Same idea here. These sets of image layers here, the basic image layers, are read-only. They are not meant to be changed, much like if you have the software and the system directories on your machine, not meant to be changed. But the read-write layer that allows this to be a container is the place where we can make changes to files, kind of like the user space we might have on one of those systems. So the top layer when we're talking about containers is that container layer, and all changes there go into that layer. So containers are not VMs. We've mentioned this before, but just to kind of help bring the point home here. If you think about a VM, a virtual machine, and you may have, I'm sure you probably have run into some of these, either in your own use or maybe at your company or something. Virtual machines for a long time were the main way that people did this sort of thing. A virtual machine, though, requires a program or a layer to run it. It's a thing called a hypervisor, fancy name for we need a program to sit on our computer and be able to host this virtual machine on top of the computer's operating system. It's called a hypervisor. VirtualBox is one. It also needs a guest OS to create isolation. So you can see kind of on the left-hand side here, we've got our server, host OS, hypervisor, then any kind of guest OS and runtimes and applications in there. With Docker, really what you have is you have the server, you have the host OS, and then you have Docker sitting here. And again, the idea with Docker, a way to think about it, is that it's actually carving out system resources. We're going to talk more about that in a minute, to give to an application that's running inside of a container. So because it doesn't require the hypervisor or guest OS, Docker is going to be faster to start up. You don't have to incur the overhead of running the hypervisor there. It's going to be more portable. It can run unchanged in multiple environments, and generally is a better solution if you don't have to have a really high-powered sort of system running multiple applications. Most containers are targeted towards a single kind of application or a single environment there. So as opposed to the virtual machine, again, Docker is more lightweight and more portable typically. So let's see if we can get this to actually go. So here's an example, and it's a little bit hard to see. I apologize on the slides. But on the right-hand side here, I'm running a little command here, which is just a Docker build command. What this is doing is it's going to take the instructions that are in this text over here on the left-hand side, an example of a Dockerfile, and it's going to go and execute them. So what it's doing right now is it's going through and it says, I'm going to go, and the first instruction here is from MySQL 5.5.45. What does that mean? Well, this simply means that I want you to go out, get an existing image that somebody else has put together that has an operating system and an environment for running a MySQL database system. So someone has put together, spent time to put together an operating system, put MySQL on top of it, and layer that on top of it and have it all ready to run. Now that's available for you to use. You could pull that image, you could run as a container, and you could run MySQL on your machine. You could have or in the container. So that's pulling it down. That image itself was the result of somebody putting a set of layers together, laying down the operating system, layering on MySQL, setting the environment. So what happens when we tell it to do that, the from says go out and get that image. Notice this 5.5.45, that's a version number on it. And it says pull complete, it's pulling down the different layers. These funny looking, the hexadecimal character or strings over here, these are IDs. It's pulling down the different layers that are part of that image. And then we go and we say copy over some stuff. Again, the idea of copying over some local files. I'm creating my own image here. So what the Docker build command does is it allows you to follow the steps in this Docker file to put together an image that you want with the things that you want in it. So we go ahead and then we copy over some files. Do you see that? Maybe you can. In step 2 of 4 here, copying over some stuff. And then you'll see it actually does endpoint here and a command. This is basically telling it, this is what I want you to start running. When somebody starts this container, go off and execute this command and execute this script in there. So again, containers have this idea of a primary application, single application usually, to run when you start running the container based on what's defined in the image. So how does this translate? Well, at a different level here, if you were to go and look at the history of what went into this, you'd see a set of layers. And basically, if you look at the Docker history, maybe kind of hard to read, there's at the bottom here, there's a couple of add files, set up a MySQL group, make a directory for the entry point, do some apt-get updates. These are all the same kinds of things you would do if you were installing this on another computer, on a real computer. You're just doing them to put together an image. So this stuff here that says where it has missing because they don't have the IDs for when it was created, these are all the steps that somebody went through to create that MySQL base image. When you're working with images, you're creating your own image, you're going to have a base image typically that you start with. That's either going to be just an operating system, or in this case, something like an operating system with an application already configured to be usable in there. So then we have the different layers that we created based on top of that for the different commands that were executed in the Dockerfile. So to give you an example here, we said the first one was to pull down from the MySQL. So you can see the colors here kind of coordinate. We start creating our image over here on the right. And then as we go and run the next set to copy over something, that causes an instruction to be executed when Docker's building the image with Docker build that says copy in some local files. That creates another layer that is stored in the Docker area on your file system and creates another layer there for this particular image. And then likewise for the endpoint and also for the CMD. So we can think of these different commands as basically creating different layers that come up that create the image. So eventually then we get from this process, from this Docker build, an image that we can use for a container. So we've got the base image there, and now we've got the base image. And when we talk about the layers in here, layers are basically like operating system or files to the OS, meaning they can be combined together to form the image. They're read-only, as we've said. And then to create a container, again, what we do is we do like a Docker run command. That's an example shown here, Docker run. It's a little hard to see. But basically what this says is Docker run -e MySQL root password, and then it runs the image and creates a container for us. So somebody has created this image that has MySQL, that has the operating system, and they've also done things that said, okay, to make this more applicable widely, to make it more generally usable, what we need to do is we're going to give them a chance to pass in an environment variable like the MySQL root password, or to maybe it'll be the database that they're interested in. They'll give you a lot of times ways to set things with environment variables, so when you pass it in with like a Docker run command or something, you can actually then customize it for your use. So at the time you run the image to create the container, you pass something in or set environment variables in a way that then the image understands. I'm supposed to get my database, which database I'm using from this environment variable. I'm supposed to get the password from this one, that sort of thing. So it makes the images more widely usable and allows you to customize them. So in that scenario, when we actually do a Docker run, what happens? We get a new layer in here, which is this read-write layer here. So it's the one like the user space that we can use to create our content. Now, a couple of the operating system constructs that allow these containers to actually work and function as you expect, among them is this thing called the union file system. Now, union file system is basically a fancy way that says, I want to be able to look at a place, look at a directory. If something's not there, look at a different directory. If it's not there, look at a different directory. Simplest case I can think of, or simplest way to explain it, think about the path variable. We've all probably set the path variable at some point when you installed software. You know how that works. You have a path variable on your operating system that says, if I don't find it in this directory or this place, then I need to go and look in the next place that's in the sequence. If I don't find it there, I go and look here. So depending on where things are in your path, that's the order that it searches. Same kind of thing here. The union file system is this idea that as we created these different layers, as we executed those commands, and we have different layers with different files, different configurations that make up the image, then the union file system allows us to kind of look top down through that to find files. So it looks kind of from the top down and says, if I don't find it in this layer, drill down to another layer, and then drill down to another layer, and so on. So that works really nicely because then we can get to any of the files in there by drilling down through here. Now, one of the questions that comes up though is, okay, Brent, you said that this is read-only, these immutable layers here of the image are read-only, and then the top layer is where we can read-write. What happens if I want to change one of these files? How does that work? Well, it turns out that there's a process called copy on write, or CAL for short, which what it does, if I need to change a file here, let's say I want to change this file, then what it does is it actually copies that file up to the top level, up to the top container level. Because that top container layer there is where we can read or write. It's kind of the same idea if I wanted to, for example, change some file that was in a system directory that I didn't have access to change on my computer. I could copy that file over into my user space, my home directory, and make a change to it there. But the system handles this for you automatically. So it's a copy on write, pulls it up to that top level layer, and then you can make changes. And because we have the union file system, it can drill down. It starts at the top level, so it finds that new version before it finds the one below. So that's an example of how we're using these operating system constructs to give us this kind of container functionality. We copy the file up, and then we can do it. We can do it from there. Other Linux facilities like C groups and namespaces are there to help kind of handle some of the other resources we need in containers. We'll talk about them in just a moment. Now, the cool thing, one of the reasons that we have the immutability here, or one of the benefits that it buys us, and immutability again just means that those lower layers below the container layer are read-only. The nice thing about that is that we can create multiple containers off of a single image, okay? The difference is the image is those set of layers. The container is adding on that other read-write layer. But there's nothing that says I can't have multiple layer read-write layers on there that pointing back to the same image. We don't have to worry about things getting changed because these are immutable here. These are set up in here. So we can just set up a new container by pointing a layer, a read-write layer to that. It's the same sort of concept if you think about having multiple users on a computer. You have multiple users. Every user has their home space or has their own login area there too, but they still can share a common operating system. They can still share some of the common system areas too. So it's the same kind of idea. We can have this set of things that never changes, so we can just add these other areas here. In fact, you could almost think of these almost as like the user space or a home directory for different things to log in. But this is really just, you can have as many containers as you want based off of a common image. Now, this also applies that we says these images, these layers here, are actually stored on the operating system. They're stored independently. Even though any particular container has a certain arrangement of these layers, the layers themselves are stored independently in the Docker area on the file system. So that means that if I go to pull do a Docker pull here, Docker pull means get something out of a registry, get an image down. Then if I do that, then basically I get the layers down that I need. I get the layers that are associated with that image, and they're pulled down. If I then go and do another Docker pull later on, and it happens to use some of the same layers, we don't have to get those layers again. The layers only need to exist once on the file system there. And then the image tells it how to tie those together. So that's a nice feature too, is basically multiple containers can share access to the same underlying image, and only layers that change need to be updated. So if I'm building a new image, but I have the basic layers already there for some of them that I need, I don't have to change them. If I use the same, I pull down say an operating system, Ubuntu 18, and I want to make a couple of containers based off of the Ubuntu operating system, I can use that same layer there, and it can then stack other layers on top of it that change. But that actually saves us some, it makes it more efficient, makes it more convenient. Docker uses, so I went through that a little quick, Docker uses storage drivers to manage the contents of the image layers and the writable layers. So the storage driver is the piece of the operating system software that ties these things together, that tells it how to connect these things together and how to make it all work. So we've been tossing around Docker. What is Docker? And this is sort of the PR speak here, the marketing aspect. Open platform for distributed applications for developers and sysadmins. Open source project to ship any app as a lightweight container. Basically, Docker was the first one to really get out there and take these different underlying operating system pieces and make them easily accessible, to make them work as a system so that we could create images and orchestrate things and do it easily. Provide a REST API, a REST interface, provide a description format for how containers should be put together. They kind of tried to stay standardized it, and for a long time, they were the main player in this space. They were the ones who were leading the way, and it was a big deal. In fact, a lot of times you would hear people talking about Docker almost synonymously with containers there. Not the case anymore, but that traditionally, historically, that was pretty much Docker was leading the field in this area. In reality, what Docker is, just a thin wrapper around some Linux container technology. So the Linux operating system has a set of core technologies in it, LXC, Linux Container Technology, and it leverages three functionalities, or things like Docker leverage functionalities from Linux to provide this isolated environment. Things like the union file system, we saw that drilling down through the layers. The namespaces, we'll talk about that in just a moment to kind of restrict the visibility, and C groups or control groups to manage resources in there. So what Docker is doing is really just leveraging or kind of wrapping around these core technologies and putting them together in a way, they're using them together in a way that they can then create the images from it. So let's take a little bit more look at a couple of these technologies. I don't want to dive too deeply into it, but to give you kind of a better sense of it. C groups or control groups. This is a Linux feature that allows groups processes for the purpose of system resource management in there. Tracks, isolates, limits resource usage. It's basically taking some of the system resources and just putting them together into a group here. So if we think about it from the standpoint of things like CPU, memory, I/O, networking in there, you might think about it if these are a pie or a circle there, taking a portion of these and then putting together into this control group or into this C group that is then used for the images and for the containers here. So again, you see it's the idea of getting pieces of these things, kind of carving out those operating system resources and putting them together then to be used. Windows actually has a variant of it called job objects. Windows has been doing its own thing with containers, trying to kind of catch up with it. For a long time, they would do things like letting you run containers in virtual machines. They would have Linux virtual machines that would then do it because the foundations of containers, again, were based off of these Linux technologies. Now Windows has its own native container functionality, which kind of is getting mixed reviews right now, but they're still trying to work on it and move it forward. Namespaces are another operating system feature leveraged with containers. Isolated instance of a global resource appears as a separate instance. Windows has its own variant called silos. So these are things like process IDs, the IDs in the operating system of the processes that are being used there. So when we talk about it with containers, it allows processes in different containers to have the same process ID. If you think about it from the standpoint of an application running within a container, again, this idea of it's running within its own, as far as the application is concerned, its own little computer, its own little environment there. It might have a process ID 1, process 2, process 3, and so on. Another container would allow it to have process 1, 2, and 3, and so on. So this allows it to separate those out. Process identifiers and a list of processes. Networking provides isolation of network controllers, system resources in there, firewalls, and routing table. Again, this is all about taking those general system resources and carving out sections of them or portions so that different containers can have sets of the resources themselves. Mount points in there isolates a set of system mount points connecting up the spaces or the disk there. Interprocess communication such as message queuing, system objects and stuff. I won't go into too much of a detail here, but again, I'll get you access to a PDF of the slides, so you'll have that information there. But the idea is that it keeps things from kind of stepping on each other, keeps them from trying to, memory from stomping from one container, from stomping on another container's memory. User space allows specifying a list of host user IDs. In other words, a process can have full root privilege for processes inside the container and be unprivileged for operations outside the container. What that means basically is they can keep the container, they can keep the processes inside from doing things they shouldn't on the machine where Docker is running. The idea is within the container, we might need processes to have more advanced privileges, to run as root, for example, or to have a high level of access. But we don't want that process to be able to touch something on the host machine or the computer that's running Docker or hosting the containers, so we have to restrict it inside. That's what this one is about. And finally, UTS is basically node name, domain names. Each allows each container to have its own host name. If you think about from a container point of view, like a computer, if you log into a computer, it has a host name, that computer's name in there. So this just allows the different containers to have their own individual names in the system. So this is an example in namespaces, kind of the ways that Docker and the other things that implement this limit or set up or split the system resources out so that each container can have its own set. So what is a Dockerfile? We talked about this briefly, and going back to how we create the images and such. It's a way to create a Docker image. It's a plan. You can think of it as a series of steps or a recipe. Again, the way I sort of think about this, it's most easy for me or to explain it, is if I were to ask somebody to set up a computer for me to install software, I might say, please start with an operating system, then copy over some files from this USB drive I have. I want to carry them over from the computer. I want you then to set up an environment, that sort of thing. It's a series of steps. And what it does when we run that Docker build command is it goes through and just executes it. It gets the things that we need, lays down the operating system as a layer, gets the files copied over as another layer, and builds up those layers to create that image, just like the disk on the computer that has everything on it set up, installed, and partitioned. Has a specific format and structure. You can see the commands kind of in all caps here, from, copy, entry point, so on. And each instruction in Dockerfile can create a read-only layer. Not each one is going to. Used to be the case that was more common, but these days they've got more efficient about it. So it doesn't have to create a new layer for everyone, but most of them will. So kind of giving the big picture here, on the left-hand side, we have an example of a Docker file, which is going to be used to put together an image. If we run Docker build, then we get what that does, it just executes the Docker file. It says, hey, I'm supposed to go out and get this image, bring it down, create that. I'm supposed to copy stuff down. I'm supposed to do this. And eventually, think of it as kind of automatically provisioning, automatically setting up that disk for you. If you were to have something, if you had somebody else doing it, you hand them a list of what you want on there, what you want installed, how you want it configured, and they go off and do it. Same kind of idea. It just goes through and creates those layers. And then once we have that image, we can do a Docker run to actually run the container, which all that does is essentially say go and put in this read-write layer on top of it. Docker has a built-in set of commands that you can use, things to look at what's inside of it. Docker inspect, look at the images. Docker port, see what ports it is, look at the history of it. All these kinds of commands that you have to work with this. Again, Docker is sort of that wrapper, that application that wraps around those technologies and makes it possible to construct images, create containers, and those kinds of things. I won't go through all those now. So how do we think about this? Well, we talked about this already, but to try to give you the kind of visual here, the analogy of installing software, provisioning systems. If we were to go through and set up a computer for somebody, layer on the operating system, maybe some Office applications, and then like an antivirus, we stack those things up. We build up the layers of software on the system. At some point, we have a disk image. We have an image then that we can save off, and we can then use to go through and provision another machine. If we had somebody that wanted the same kind of machine set up, we could take that and we could take that image, install that, use that software. And then if we want to think about actually running a container, when we run a container, it would be kind of like creating that user space there. That user space, that read-write area. They're running the software, we've turned the computer on, the stuff that's installed on the disk. The disk is there whether we have the computer on or not, right? So an image is there whether or not you're using it as part of a container. It's just a set of configured software. When we have that then, If we were to add the user space there, that's kind of equivalent to the idea of having that container layer that we could create from that. So the idea of sort of a simple way of thinking about it. All right, so Docker on Windows and Mac really quickly. We've talked a lot about using it in Linux. Once on a development system, the user runs the Docker host where Docker images are deployed. On Linux or Mac, the host has typically been Linux-based. That is, it only allows creating images for Linux container. Mac uses a thing called HyperKit and a virtual image. Docker Desktop is a package that's available for Windows. Was free. They're going to start charging for it in January, or at least for large enough users. Host containers in a dev environment provide some additional tools. So the Windows containers, so the Docker Desktop is for kind of working with containers, the sort of user containers we've been used to in the past. And Windows containers has two types of runtimes, Windows Server containers and something called Hyper-V containers. So as I said, Windows has kind of tried to catch up and they want to get their own version of containers as well. So now they're getting with that. Reviews on it that I've seen have been kind of mixed as far as the native Windows containers. So I think a lot of people still continue to use things like the Docker Desktop or just go to a Linux system in that way. So your mileage may vary, but they are making strides into that. All right, let's go and talk quickly here about diving a little bit deeper into layers. Containers can reuse layers. We mentioned that when we pull things down, layers get stored on the operating system as structures there. And then when we go to actually pull down other images, if those images happen to be using the same layer that's already existing, then we don't have to pull it again. So you may see things when you're pulling it that already exist. We pulled it in the first case for that first image, but then when we tried to pull a different image, we actually didn't have to pull all the layers. So we can reuse those layers that are stored on the operating system as a component of another container. Mapping layers to the file system. So we talk about, this is just to kind of give you an idea of sort of the physical mapping. When you're talking about these kinds of concepts, I find sometimes it's a little bit easier, even if it seems a little bit too technical, maybe to kind of try to help explain how things are actually stored or how it's actually happening. So this is just a little bit of information on how things are actually happening on the operating system side. Prior to Docker 1.10, we had a layer is essentially a delta or a diff, meaning that if we had a Dockerfile instruction that said add a file, then the layer before that would not have that file, but the next layer, the new layer, would have that file. So as we're making changes in the Docker from the Dockerfile, the instructions can create new layers. So we have this information that kind of keeps track in the system of what's in that. So the new or changed files, as we went through and did things to build up the image, would be stored in a different layer. Prior to Docker 1.10, images and layers were synonymous. What we mean by that is that in the image, if you were to look at it, you would see that set of layers stacked up there for an image, and they have their own unique ID, this DC89 or EAD, whatever's in there. So we have then a set of layers, each one with their own unique ID. And then if I was to actually go out into the operating system and look at where Docker was installed, var live Docker in there, you would see that there would actually be physical directories with the same name as those different layers. Docker just simply stored the same layers in there as the physical, or the same physical directories as layers. So there was a one-to-one mapping in there. And that was the way it was for a long time. But then what happened was there were some, if you were to inspect it, you would see that as well. You'd see the IDs and such. Docker is inspect is a Docker command to say let you look in it. Now, if you were to go after that, 1.10 plus up to the current day, there were some problems they discovered with that. It was hard to tell if something had been changed inside of it, because you can imagine if the names were just based off of just a specific name, you could go and change contents there, or somebody could hack it and you couldn't really then tell that it had changed in there. So it was hard to tell if it had been tampered with. So they went to a new approach. Fancy name is content addressable IDs. All it means is a hash, a checksum. So what they do is they basically said, we're not going to try to just attach a name to this. We're actually going to run a checksum. We're going to run a program that's going to compute a value, and where that computed value, based on what the contents are, is what we will have as the name. So it does that kind of checksum in there. Layers don't have any affiliation of an image. They're just a collection of directories and files, but they have what's called a digest. Again, fancy name for a checksum, basically, or a hash in there. So basically what they do is they go through the layer's contents and they create a checksum from that. Now SHA-256, you probably at some point have heard of a SHA value like a SHA-1 or SHA-256 or SHA-512, or maybe if you haven't heard of that, you've heard of MD5 checksums. Same idea, they're all secure hashing sort of things. They're checksums of the contents, and based on that content, it computes a value, and then that value becomes the identifier for that layer. That's the basic idea here. So then if we were to go and do a Docker inspect of an image, we'd be able to see the layers here, but the layers then are based off of the content that is actually in that particular layer in the operating system. So that way, for example, if somebody were to go and tamper with that and try to compute again, it would create a different checksum, right? So it creates a different checksum, so it would be a different name. So this is kind of a way to help prevent or help to identify things, help make sure that things haven't been tampered with. But the Docker image itself has a configuration object, which is kind of that list of layers together. They're stored in the operating system, and it uses an image ID. So the entire image is based off of a checksum from that configuration object inside of it. Storage drivers. So we talked about the idea of containers and how they're built up, how they're made. Storage drivers are the operating system functionality that allow it to be able to combine the different layers together, to be able to manage things as images and as containers. So a Docker engine has this cache or this structure, directory structure, of different image layers out there. Layers come from Docker pull, Docker build, and so forth. So when we do a Docker pull, we're getting an existing image down, we're getting all the layers that are associated with that image, and they're stored as separate pieces in that var live Docker, in the operating systems area. Then we have, if we do a Docker build, we may create new layers because we're executing an instruction that we have that may result in a new layer that's stored out there. So these layers get pulled in there, and when we go to actually put the images together, that's where the storage driver helps to combine everything and to manage this and to pull it together. So it creates kind of an image graph in there. Now, I promise you I won't read you all the words on the slide here, but what this is, these are all the different storage drivers that have been in Docker over time, have been used to create images and containers. Some of these were used for a long time, AUFS, Advanced Union File System. These are all ways that people had or the operating system pieces that said, we can combine things together, we can manage these images and containers in there. They all have had various, well, some had much fewer pluses than minuses, but what they kind of settled on now, they've gone to this one overlay 2, the overlay file system here, and we'll talk more about that. Again, you'll have a copy of the slides if you want to explore these more, but I won't bore you with all that now. So overlay file system directories, when we talk about the overlay driver, they break it up into these ideas of blocks, kind of chunks of content. There's what's called lower dir, and all that lower dir is it's basically kind of a set of these layers. So if you think about, it can have a certain number of layers there. They don't want to just have separate, each layer being separate thing, because that starts getting into a problem of using system resources like inodes, system resource having too many pointers to different things. So what they did is they said, we'll just take this set of layers and we'll connect them together, and we'll have that mapped in this what we call lower dir. Kind of like you have a path. You have a path variable and you have a set of directories, and so you have a set of things that are connected together, kind of the same idea. The upper dir is what they call upper dir. These are terms internal to the image. That's really where your read-write changes are. Merged dir is where you get the merged view. That's that sort of top-down view where you can see things kind of at the top level. I see a file here, so I don't see the one below, that kind of thing. And then workdir is used by the overlay FS. You don't have to know all this to use containers, but again, just kind of giving you a little bit of the backstory. In fact, there's even a way in Linux itself you can simulate this sort of functionality by doing a mount with an overlay driver here and then connecting these together. So let's look at a picture. I like pictures much better. If we were to look at how an overlay driver, the overlay 2, represents a container image, we could have on the left-hand side here, the container layer, sort of the top-level image layers, 1, 2, and then a base layer here. These are kind of the Docker concepts. If we were to map them to the operating system concepts, it calls it like a lower dir 1, 2, and an upper dir, and then the merged view. So in the operating system, this is kind of how it maps things out. Now, where you would see this, if you were to go in and do like a Docker inspect and look inside of that, you could see the connections in there. But again, just to give you the basic idea, you have files at different layers, right, that you construct from this sort of a dockerfile process. And then you have the merged view, which says, I see file A comes from this layer, file B is in this layer, file C in here. You see the file B here, not here, file D. So you have this sort of merged view, kind of looking from that top down. Some things are masked at upper layers versus the lower layers. What happens if we want to delete a file? Well, if you delete a file, they have kind of a whiteout file. Remember the old whiteout when you had on the typewriter? Maybe some of us do. You'd have the little white stuff, you'd wipe out. They have a whiteout file. So they basically put a marker file in there that Docker interprets and says, okay, this file is blocked. But it's still the same idea. I put something at a higher layer that masks the lower layer there. So if you happen to want to know some information about Docker storage, you can do a Docker info, and you'll see things like the storage driver that it uses, overlay 2 here. You can also then find where it's actually storing the layers. So if you were to go out and look at that in var live docker in there, you would see things like you would see directories for the containers, for images, for overlay 2, runtimes, all these kinds of things, volumes in there. These are all things that go into making up a container or making up an image in there. And you can actually go in and look and you can find the different layers in there, the different files that are stored as layers. And then again, what this does, it just weaves them together into this image that makes up a container. So real quickly here, let's talk about a couple of Docker alternatives and some things that you should be aware of with this. As I said, Docker was kind of the first one to really sort of formalize this, to set up the image specifications, to put a REST API on it, to have commands built around it, those kinds of things. But when, over time, they worked with in 2015, worked with the Linux Foundation to be able to create this OCI spec, Open Container Initiative. Essentially what this meant was that Docker worked with the Linux Foundation and said, hey, we are going to share the specification. We are going to share the image specification, the runtime specification, and how to bundle things up from the file system to create these images. And the net of this is then, if you follow this OCI specification, you too can be like Docker, right? You too can manage images, you can manage the containers. It's great in an open source environment, open source, when they do this, because then it allows for a much wider sort of field of these other applications that can do the same thing. And because of that, there's competition, right? And you can get better sort of performance or better to drive each other. But so OCI basically is this shared or this common specification for the runtime, for the file system, all the sorts of things, or for the image that will allow you as an application, if you follow the OCI spec, to do what Docker does. So that's led to quite a few other programs out there. Some of these are older than others, but Podman, Builda, Rocket RKT, Cryo, Runc, Kaneko. I won't take time to go through all of these, but some of these you'll see more than others now. Rocket is one that's been around for a long time. Builda, Podman, and Kaneko are kind of newer ones out there. you'll see there's more, actually we're seeing a shift from Docker being more dominant in there to actually being much less dominant. They're kind of struggling a little bit to figure out where they fit these days and kind of how to do the market share. As a result, you kind of see some things where Docker's monetizing things more honestly in terms of they have pool limits or Docker desktop now things come for a cost. Other systems like Red Hat with their Enterprise Linux 8, they ship with, I believe, Podman and Builda now, or maybe just Podman, but they don't even have Docker available anymore. The same ideas that we've talked about apply with the images and containers. That's why I went through the Docker one, because that's more, it's a little bit easier to understand because everybody's pretty much heard of it and stuff. But these are players in the space now. A quick note here about Docker security. When you run containers and apps with the Docker, it implies running what's called the Docker daemon, or daemon, depending on how you say it. And the daemon is responsible for state of container in the images, require interactions with external processes, but it has to have root privileges, or at least it did. And this was always kind of a security concern there, because what it would do is create a socket or a communication channel to the Docker for the Docker group. So then CLI, the command line interface, when you ran Docker, would talk to this daemon, but the daemon had root privileges. So for a long time, there was a lot of concern about this, because if you were running a local Docker daemon, then any process that were to break out of the container, sounds weird, but if we think about something that, for whatever reason, got access to a resource on the computer where it was running, that was going to be a liability, that was going to be a danger. So any process that broke out of that would have the same rights as the host OS to do whatever they could do on the host OS. So now, as of version 1903 of Docker, they have a rootless mode available, so they don't have to run as root anymore. Anytime you start going into running containers and like doing things in Kubernetes, which is a way to orchestrate containers, what you'll find is that there is a real concern about the privileges. And there are all kinds of things that we don't have time to talk about, but there are all kinds of settings about how do we run our containers with appropriate privileges? How do we restrict what they can do? How do we make sure they can't go out and modify things on the host operating system? So I'll just put that plug in there, and I put the slide in here. If you start working with containers at any serious level, one of the first things you should probably do is start thinking or start trying to understand more about how to keep them secure. There are things you can set in the Docker file for a particular user to run or for permissions and those kinds of things. So, you don't want to have your container just always being available, have run as root out there. So you have to keep that in mind. So something, just a little plug there to think about. But Docker at least has a rootless mode now. We don't run as root, and it requires some extra setup in there. The Open Container Initiative, just a little more about that project of the Linux Foundation. Linux Foundation, if you're not familiar with that, something to go explore, take a look at. They really made an effort to define open standards for a lot of the things and to make it more accessible. It really embodies the kind of the open source software initiative there. I'm not saying it's perfect, but they are trying to do that. So the OCI allows containers to be used by multiple runtimes, includes runtime specs, provides better flexibility, and so on. It's based off of a particular version of Docker schema manifest, version 2, schema 2. So some older container stuff might have some issues with that. Builda, alternative to Docker, similar commands to Docker, allows for building images without a Docker file. Basically, from the Builda command line, you can specify what goes into your image without having to have a Docker file there. Provides a command line interface to build either traditional Docker images or the OCI versions. Podman is another one, specializes in managing entire container lifecycle. Some commands are similar to Docker, but not all. It allows you to create pods. What pods are just groupings of containers. It's more of a Kubernetes term, but basically, if you think back to the example I had earlier on, the picture with the containers in their container cargo ship, and I said the mascot for Docker was the whale. Well, what's a group of whales called? A pod, right? So they say a pod is the group of whales, or a pod is a group of containers there. And Kaneko is another one used to build images without root access. Basically, it builds stuff inside of a container. Or images are built inside of a container or Kubernetes cluster. Sounds weird to think about building an image inside of a container, but if you think about a container as being that space where you have everything set up that you need, then you can do it inside of there. You don't have to run things on the system itself. You're just running the container, so you can use that then to build the images in there. That's supported by Google. All right, I've been rambling on for so long. I apologize, but thank you for your attention. Questions? Anybody still awake? All right, you're laughing, that's good. All right. Yes, sir? So the question was, and I'll try to simplify this. Basically, with Podman, we said they use the concept of pods. Pods are groupings of containers in there. And I think the question was basically, can you run any kind of set of containers inside of a pod the same way you could, say, in an application like Kubernetes, which allows you to run pods? Yeah, as far as I know, you should be able to do that. Anything you could effectively do in there, as long as you could set it up the same way. Now, Kubernetes with pods, they have ideas of things like init containers, which are initializing in there too. I don't know that Podman goes that far with it, but if anybody else wants to chime in, feel free. But as far as I know, you can group any kind of containers. I don't think it has like the dedicated, this one is an init container, or this one is a sidecar, that sort of designation. Other questions? Did we have any online questions? Right. I have put everybody to sleep. That's good. All right. Yeah, it absolutely is a lot of information, and I apologize if it comes across as sort of this tidal wave of stuff. Again, the idea is not that you understand everything from this, but I want to at least get you exposed to the ideas and get the ideas out there and how things work together. And then you have to kind of chew on it for a little bit, think about it and stuff, and then hopefully at some point it comes back, oh, that's what he was talking about in that context. You know, the basic idea is, though, with that containers, they have self-contained environment. We can use the dockerfile to have the set of instructions to set it up. We have, they're built of layers. The layers are basically a set of the changes that are executed from one of those commands in a dockerfile, set of changes, files, directories. Those layers are stored on the operating system, and images can be created from those, and the container is basically just a running instance of the image with that read-write layer. Clear as mud? Yes, sir. So the question was, are containers read-only? Containers themselves, you can read and write in, but the image that they're based on is what is read-only. So the image layers is what, when we put the image together, again, if you think about kind of like installing software on a PC, you lay down the operating system, you lay down the other applications, you're normally not writing into those directories. You know, you don't have permissions a lot of times to change stuff in the directory. So it's the same idea. There's a base layer of those of the programs, the applications, the environments and stuff, and those are read-only. From that, then, you can make multiple containers, and the containers are simply, all that means is we're adding another layer that is read-write, much like you might set up a user space on the computer. You know, if you have you have your own home directory when you set up on a computer, that's your space to read and write in, but it still uses the files that are installed and the operating system and such. So containers are a running instance of an image. The image is read-only, but the container itself has a place to make changes. So it's read-write. Yeah. Yes, sir. question was, I think, if you have an app inside an image, it's almost impossible for someone to access that or to get access to that. Is that the, basically, so a couple of things, and if I don't answer your question, let me know. So when we talk about things in the image, they can run in that environment. They can run and execute in there too. Now, if you want to have the app create files or something, you could have it mount, you could have it connect in a disk space and say, I want you to write something out to that. So at the time you create the container, you can have it say, I want to mount to Brent's file system on this machine or out here in there. Okay, so unauthorized. So you're saying basically, if you have an app inside of your image, it's impossible or it's difficult for it to have unauthorized access? So the question was, is it possible to have unauthorized access in there to have access? So it kind of goes back to what we were saying at the end with the root privileges there in there. You have to take into account what your application can do and kind of restrict it. There are various ways to do that, setting the permissions on the applications, setting who they run as. For example, it's possible that you can set an image or an app container as something called privileged. And privileged means that I can go and then have access to resources on the host machine. Not a great idea. Most people don't want it. They don't want it to be privileged. Or your application, if it had permissions, it might have permissions to go and write stuff to a file system there, connecting into it. So in that sense, it's doing things. It can access resources out there. So you have to bound it. You have to sort of put these permissions on it, or there are other things around it you can set, like in Kubernetes, there's things like they call it gatekeeper, security context, constraints, these kinds of things. And that's actually a big deal when you're talking about running these containers in larger systems like Kubernetes and such, because if you have a client that says, I'm going to take your image, or I'm going to run it on my system here, they want to know that you're not going to be running as root because they're going to be, or you're not going to be privileged because they don't want your stuff to be able to touch their external stuff at all. So you have to be really cautious of that. Now, if you're actually running stuff in a software as a service environment where you have control, you don't have to worry about that as much. But yes, security, you have to do things specifically to make sure that your application is only going to run with the privileges that it needs. Yeah, absolutely. Any other questions? All right, I think that's it. Thank you, everybody. Really appreciate your time and your attention here. I hope it was useful to you, and I hope I get to see you again sometime. Thank you.